testing in this current section of the course. And today we're going to be talking about patching, which we didn't get to last time, and fixtures. And both of these are going to be very important to understand going into the next task, which is all about writing unit and integration tests. And so we're going to try and make sense of these concepts. And today you can actually work as groups of 4. It's OK to work as 4s, but I would encourage, if you're at a single table, when we get to the point of, well, actually at this exercise, as we're starting to warm up, this is the context we left with. We were looking at these 2 classes, a list storage class and an underlying text file IO class. The text file IO's purpose was to just read and write some text to the disk using path, which we learned was about file paths. And so this allows us to save information to the disk. And then list store is just a little layer above that for thinking about how we store lists of strings and work with them, and we can add to them. And of course, these are incomplete examples and very simple with the purpose of trying to get them onto a single slide and be easy to reason about in a short period of time that we have together in class. So your warm-up question here, and what we looked at was how would we actually unit test list store, right? And what we did was we mocked text file IO, and then when we created a new list store, we used that mock as the input, or as the argument for IO when we constructed a new list store. And so we just mocked out the underlying behavior for text file IO. And today I want to go in a direction that is a little bit more challenging. And I want you to take a look at text file IO and think, OK, well, how would we write a unit test for its read method? This seems a little trickier than writing a unit test for the add or the items method of list store. And the first question I'd ask is, what would you need to isolate? And the second might be, how would you actually go about doing that? And we won't spend too long on this because this is what we're about to reveal to you, but I want you to think about what would you need to isolate in text file IO to write a true unit test so that we wouldn't actually hit the disk or anything like that when we tried to read or write files, but we could still test the behavior as units. So talk about this briefly at your tables. And if you're at a single table, try joining up with a table of more folks than that. And jot down your ideas on a whiteboard. 30 more seconds to talk about this as a group. 30 more seconds. All right. I'm seeing a variety of answers. We're talking about making some mocks. And yeah, ultimately, there's going to need to be some kind of mocking behavior here. But the challenge is, and I think this, so the fundamental question is, what do we need to isolate for testing read? Let me switch over to my iPad really quickly. And there we go. We see in that with block that we have, this file name, right? And so let me get a color that's visible. Right, so file name, when we set it up in our constructor, that's a path, right? And so path was something we imported from Python standard library. And so when we have this path object, we call its open method, and we get a handle on this file handle that allows us to read from it or write to it. So we do want to mock this open behavior somehow. Like we want this to actually return something that we could then call read on and expect some content back from it. But it's entirely unclear, based on what we've talked about so far, is how would you actually mock that or get that to work? Because what we've seen so far with mocking is that, sure, we could mock text file I/O and we can construct a new list store in that way. But this dependency, is an underlying package that we've imported. We're depending on directly. We're not composing anything here. We're not setting up this implementation of path isn't something we can substitute in our constructor. And so what we're going to learn about today is the idea of patching behavior in, which is very common in a scenario like this in Python, where there's some underlying behavior that a function or a method depends on, and we want to patch over that to have control over it, to run a test and isolate the unit that we're looking at and make sure that our logic's correct. And so to motivate this, I'm going to step away from this example. We'll come back to this and see how this would be done a little bit later on. I want to think about this example. How would you unit test this particular function? So and I apologize on the board here, this blue is a little hard to read. Let me see if I can get the lights down. But we're importing the random package from the Python standard library. And this function is just one where if random.random, which will return a number between 0 inclusive and 1 exclusive, if that is less than 0.5, then we will return heads, else we will return tails. How would you write a unit test for this function, right? You could imagine, and so what would a unit test mean in this case? It means that we're not actually going to test the random behavior, right? We want to isolate from that randomization. And so what we want to be able to do is patch in some behavior so that we can say in our test, random when our function calls it, it's going to return, 0.1 or something, or 0.67, whatever it is that we want it to return. And we're going to look at what that return value is compared to what we expect, and that's how we can unit test this given function. All right? So in Python, we're able to do something called patch a name because it's a dynamic language. And if we were to look at its memory implementation, like at runtime, everything that we import or define in our program is actually something we can reach by strings and like looking at dictionaries almost and tracing our way down some attribute chain to, random.random is something that we can actually override in our Python program. So what we're going to do is we're going to pick some name that we're going to patch in our program. In this case, it'll be random.random. And we're going to, before we replace it, we're actually going to grab a temporary, set it up a temporary reference to it so we don't accidentally overwrite it. We'll have some temporary storage that says, hey, for the time being, we're gonna reference the original implementation in another way so that we have a handle on it. It's like swapping two variables like you would do in 110. So we're going to keep a temporary handle on this, and we're going to momentarily replace this name with our new implementation, right? Our new implementation might be a function. We'll also take a look at how we might do it with a mock object, and that's not too difficult either. And then once we've gotten through the act stage of our test, and we only really do this for testing purposes. This isn't something you would expect to do in a program for the most part, but it's very common in tests. We'll restore that patch name with the original implementation. Right? So let's take a look at this in pseudocode. So if we were doing this ourselves and we didn't have a library or anything to do it with, this is what it would kind of look like step by step. But I want to point out that this is not exactly how the library does it behind the scenes. It's a little bit more, it takes care of some more complexity than we're handling here. And so you would never really go about it in this way. I just want to point that out before, like the point of this slide is really to just show you what's going on, the mechanism that's going on behind the scenes without the simplification of it. So in the first line, we're setting up a temporary variable. And this one's interesting. If you haven't played around in Python with the notion of assigning to a variable a function, that can feel like a confusing idea at first. But functions, as we illustrated in COMP423 in our memory diagrams, are objects that live on the heap. And you can define variables that refer to those same function objects. So you could have multiple references to the same function name or function definition in your heap. So that first step is we're setting up the variable original random to be a reference to the implementation or the definition of the random function that's built into the Python library. And then we're defining a function that's very straightforward. It always returns 0.1. Right? So this is the function that we're going to use as our mock or our substitution. I guess I would call it a fake in the sense. It's a fake implementation of random that always returns 0.1. And then notice what we do on that third line. On that third line, we're patching in our behavior. Right? So here we're actually saying, at this point in time and moving forward, whenever someone references random.random, we want it to actually refer to our function always 0.1. Right? So we're swapping this function definition in so that if I were to, the next time random.random is called, we're actually going to call this function here instead. We've just overwritten the currently bound name random.random to be bound to this function. So we then go and we act, we call our coin flip function. We would see that execution goes into that function, and inside of it, it calls random.random. And it has the effect of calling this function that we just defined. It will return 0.1. Now, before we go on to assert that we got the result we expected back, the other part of patching and testing is we need to restore that original behavior. We want it after this point, like after we've actually called this function that we're testing, we want to restore the original implementation back to working order. We don't want to break the notion of random from here on out in our program. So we just take that temporary reference we made on the first line, and we assign it to our random.random name there. And then we assert that the result is what we expected, and we're all good. Right? So this is the general concept of patching. Right? And the good news is it's much easier in practice because of some library utilities that we'll see in just a second. The patch function that's built into Python's unit test mock library. Questions on this? All right. So how does this look in practice? Well, in practice, you are going to be importing from the package or the library unit test.mock the patch function. And this patch function implements, with more sophistication than we just looked at, that exact same sort of idea that we just revealed. So notice in the arrange step, we're defining our function always 0.1, and then we reach this really fascinating syntactical call to patch, again seeing the with syntax that we briefly discussed on Wednesday. So I'm going to switch back over to my iPad here. And we're saying with patch, and then notice here's the name that we're patching. It's the string random.random. And if it feels a little icky and uncomfortable to you, that we're giving a string, and somehow behind the scenes, this patch function is taking that string and overriding some like some symbols in our program, some names to replace its behavior. Yeah, that's where there's some magic going on there. That's it's not magic. It's exploiting this dynamic language's ability to redefine names while the program's running. But it's doing exactly what we did before. It's finding that, looking up this name, replacing it with whatever we tell it to replace it with, which is the second argument to this patch function. So the second argument is the name of our function, always 0.1. And then inside of the with block, anytime any code calls random.random, it's going to be replaced with our implementation of it. And so this coin flip function calls that built in, but now it's going to return 0.1, and we would see that we get the heads as the result. Now, after that patch block completes, just like we saw before, the original implementation of random.random is restored. So if, right above this assert line, we called random.random, we would see that it's back to being whatever random number gets produced as the next number in the pseudo-random sequence. Right? Questions on this syntax? All right. I've got an exercise for you all. You all looked at and read about mocking. And here we're going to combine the idea of mocking and patching. Rather than patching with a function definition, I want you all to try just establishing a simple mock and using patch with mock instead of patch with a function definition, and see if you all can come up with this at your table. This is today's grade scope activity, and I'll have that opened up in just a moment. All right, I want to give you all a quick hint here. Don't worry about submitting quite yet. I want to give you a little bit of extra context and remind you of something that you read about and the TAs may not have read about, which is okay. I should have told the TAs, you all need to do this reading last night too. This is a new reading for us in this course. At the start of the reading, when mocking was introduced in Python's standard mocking library documentation, one of the things that they mention is you can set up, like, the first examples they give are how to mock an individual method in an object or a class, right? So how would you replace just one method in an object or class? And they showed you something kind of cool. They said something to the effect of m.mock, sorry, I'm going to use m as my variable name. M is assigned a new mock object. And if you just set up a mock like this, mocks and magic mocks is a specialization with some more functionality. That's a callable function, right? What's kind of neat about mocks is they return mocks. So if you called m, it would return to you a new mock. But m itself is a mock that you could specify its return value is 0.1, for example, in this case. And now you've got something that can be called as a function. It looks like a function, but it is a mock. And it would return to you 0.1 when you called that mock. And so you can use that as a function. And I think that's enough of a hint to give you a sense of how you would still use patch. But instead of defining a function, you define a mock, and then you use the mock. And I want to give you all a second to think through this and keep going. All right, I've just updated the submission. You can add 4 people to it. Sorry about that. And 2 more minutes on this as a table. 2 more minutes. Yep. Cool. All right, let's talk through this. So I saw a number of cool ideas for implementation here. I want to show you all just one real quick. That's pretty straightforward. If this reloads, there we go. Let me unhide this slide. Cool. So one of the things that you also read about, that this is a detail I wouldn't have expected you to remember, but when you construct a mock, you can specify at the point of construction a return value if you were trying to mock a function or potentially a method. And so here, we could have specified some random mock that returns 0.9. In this case, this is a different example. This would be the other threshold of this test, so we're checking for tails instead of heads. But if that were 0.1, it would have been 0.1. And then we do the same thing. We patch in to that name, random.random, and we're using this reference to the mock instead of a reference to a function. What the mock gives us that the function didn't was we can actually test to see that, hey, that was called in the way that we expected to. It was called once with no arguments, and you actually get some facilities that you could assert if you wanted to beyond the regular definition of a function. And so oftentimes, I think for the most part, you would find yourself patching in a mock so that you have these extra facilities for testing things that you wouldn't have kept track of if it were just a function call. There was a really cool idea of what if we mocked with magic mock random and then patched that in. And that's another way of going about it. You just have to be very careful with what name you're actually overriding. So in this case, we were very specifically overriding or patching the random function of the random module. But if you were trying to patch over the whole package, you would need to be more careful with that. Generally, you want to target the most specific thing you can. And that's going to be your best bet because that helps isolate and make sure that if there were other things that you wouldn't have expected to have changed, you wouldn't get that behavior. All right. So in a sense, this idea of patching is how we can isolate what are effectively deeper calls with some side effects. And those side effects are things like randomization. Another classic place where you would patch in behavior is for getting time, and you have certain tests which maybe are dependent on time. Well, because time is always changing, every time you run a test, it's later in the future. You kind of want to be able to override some of the timing functionalities of a program in order to say, okay, let's just assume that we were running this, today, right now, at this current moment in time, but not anchor that, or anchor that at a specific moment in time, not relative to the current time of the system. Turns out we want to be able to do this with file system calls as well. So the original example we opened up with was how do we patch in behavior for this open call to a path, right? And this is actually tricky because open doesn't return just a straight result. It returns to you a handle that then you can read from, you can write to, depending on how you opened it. Like, there's more behavior in the file handle that we get back from open than you would just want to assume could be handled with a magic mock. And so we'll see that there are some built-in, there's a built-in mock for open that we'll see is really nice. But the way that we're going to substitute that behavior is through a patch, right? So other sources of side effects in our programs when you're accessing the network. So oftentimes when, let's say you're trying to integrate with a third-party API or make some network calls, you might patch in behaviors there. And here, if you're working with standard in or standard output, and you wanted to write tests for did my program print the correct things using the print function or using the gets or some read line functionality from the command line. If you wanted to actually unit test that, you would have to patch that behavior in so that your tests weren't reliant on someone typing something into the program. So in Python, we patch these things. Other languages don't have quite the same luxury of swapping out names at runtime in the same way. But they have their own ways of doing similar things where you intercept these calls in some way and short circuit return values back. So let me actually switch back to iPad so I can try and use the highlighter on where we're looking at in this package. As I mentioned, with a function that's built into the file system, like open, or built into your operating system in the Python standard library, like open, mocking it in a way that was authentic to how it actually needs to get used would take a little bit of effort and could be error prone. So instead of doing that, because it's something that programs might commonly want to do, the unit test library actually gives you a mock for handling this scenario. And you can see that on the second line of code, where we're importing from this. This library has quite a bit of functionality built into it. That's where magic mock is defined as well. It's where patch is defined. There's a special function, mock open, that's built entirely for this use case of we want to mock the open function of a file system, and its usage should actually match the behaviors we expect, and it should still be nice to work with. The details of how you would use mock open or some of these other built-in mocks for things, like there's also one for standard I/O for reading text and writing text to the terminal. Like whenever you have to use one of these types of mocks, you tend to just open up the library page for it or engage with an LLM to remind you of what were the details and how to work with it, because they're nuanced and you don't really commit those to memory. But let's look at the use case of this. So here we're setting up our mock, and we're using this mock open function that's going to provide to us a mock for the open functionality of a file system. And it has some niceties, like the ability to specify, okay, when this mock file is read, this is the data you're going to get back out of it, right? Now notice here we create our text file I/O, and we're not composing with our mock because we can't. We don't have a way of, like, the open function was called in the context of a method definition. It's not something we composed at construction time for the text file I/O. And in the act, this is where we're going to use the patch to substitute in this mock for the open behavior, right? And so here we're saying we're going to, this is a different usage of patch, so we're going to patch an object. The path object, we're going to overwrite its open method, right? So this is very similar to if we were to have written path.open here instead. But because we have this reference to the object, this is another way of doing it, and it's actually quite nice to just override a one method in this way. We pass in our mocked implementation, and now when we call this method io.read, and time comes to, like our execution hits this point in time, well, we overrode the path class's open method with this new mock open, and so when this gets handled, when we finally get to this point of file.read, it's going to return to us, hello as our text. And so we can test that down below and have some confirmation that we have isolated this text file I/O and its read method from the underlying file system. We've substituted behavior so we didn't have to actually read a file, and we can write unit tests that are separating the concern of our underlying system and our side effects from just the unit we're testing, all right? And then because it's a mock, we can also take a look at some of its properties and how it was actually called. And you all read a little bit about this. So mocked was actually this open function, right? And then when it was called, there's also the read function called on the result of that. And you read about in the how mocking works, that you can chain the accesses to have some assertions like this and assert that read was also called once. And it would have been called without any arguments, right? So the first assertion was saying this one, that this open function was called, and then the second assertion was f.read was called. So there's some notes on the slide for this, and you'll get a chance to practice with patching in file system behavior in this way in the next task. This is the type of thing that becomes a little bit more comfortable as you play with it and get some more intuition for that. But you can see that when we're trying to write unit tests for something that depend on something in the system, rather than like compositions we made in our program, we have to use some clever techniques to isolate our unit from underlying libraries. Questions on this example? All right. So now I want to talk about fixtures, and we'll go through this pretty quickly because this is a pretty straightforward idea. One of the things you'll find when writing unit tests is you'll frequently have some redundancy in the arrange steps, right? You'll have many tests that there are arrange steps for setting up some problem look the same as other tests that you've written, and there's some redundancy in your code. Fixtures are a really great way for avoiding the duplicated code and for effectively setting up helper functions and that can generate some data or do some of the setup that you would do during arrange so that it can be reused and shared across multiple tests. We'll see that these fixtures wind up being dependency injected into our test functions. So this is the first example of many that we'll see in the semester where dependency injection is a big idea that's used for composing functions and or objects in our programs. We use a special decorator to denote a fixture, so you'll see this in the next slide, pytest.fixture. Right, so what does a fixture look like? Well, let's imagine we wanted to, we're back to thinking about our list item or our list store, and we wanted to mock our I/O system that we just played with. And we looked at an example on Wednesday where we set up a mock and we set its return value for reading our data to be a string with 2 lines in it. Here, apples and bananas separated by the new line. Right? So you can imagine wanting to use this same fixture across many tests in your test suite. So how will we actually use this fixture? It's kind of clever, and it's also kind of scary the first time you see it because it feels wrong based on what we know about programs and designing them, right? So the way that we would use this particular fixture or its returned value in a test is we would specify a parameter, with the big idea being that that parameter's name is the same name as the function that our fixture was defined with. Right? And this feels weird because you're taught that parameter names only should matter within the context of a function. They don't matter outside of the context of a function. That's a general principle of defining functions is these names tend to only matter inside the context of a function. But it winds up being a clever facility that PyTest makes use of in order to bring these things together with minimal syntactical overhead. So if you have a test that wants to make use of a fixture's return value, all you have to do is reference it as a parameter to a test. And what happens is when PyTest goes to run this test, before it runs the test, it sees, oh, there's a parameter expected here. Let me find a matching fixture that's been registered with me. Let me call that fixture, and it's going to evaluate that fixture, get the returned value, set up a brand new magic mock. So if you reuse this in multiple tests, before each one of those tests, this fixture would get rerun. You get this new object. And then you can make use of it, typically as part of your arrange step. And so notice that we use that directly, but we don't have to repeat that logic of setting up the magic mock, setting its return value to be what it is. We can use this in many different tests, and it simplifies our tests. So it's a way of avoiding repeated code in the arrange step of our tests and sharing them across multiple test functions. Questions on this idea? All right. There are some built-in functions, and the one that I want to tell you about because it's important and you'll be making use of it soon is the one we'll be taking a look at is temp path. Now, if you imagine you want to write an integration test with our file IO class that actually reads and writes real files, It's pretty common that you want to do this in such a way that you're not creating files in your source code directory or somewhere in your project. You want some temporary space in your system that will be set up when the test runs and then cleared out when it finishes, whether or not the test succeeds or not. Like, you don't want to have to always delete your files before you rerun your tests or things like that. And so temp path is actually super handy in that what it will do is it sets up a temporary directory in a space of your operating system that it's designed for temporary files that will begin and be available to you once your test starts running. And then once your test completes, it will take care of cleaning that up on your behalf. But this is one example of a very nice temporary file or fixture that can be used. And this one feels like it's crazy magic, right? Because temp path is not something we defined anywhere. Where does this even come from? Well, that's defined by PyTest, and PyTest already has that registered as a fixture that's available to you. Similarly, for doing some things with capturing standard input and output, there's some facilities there, right? When you define fixtures, there's a file named comptest.py that you can place those fixtures in, and they'll be available to any of your testing files. So I'm going to finish up the next task and post that for you all to get started on over the snowy weekend. It'll be due later next week. And then there's a reading on using AI and how that impacts learning when coding. Have a great weekend and enjoy the snow.